All right, let's pull back the curtain on something pretty ingenious in electric vehicles today.
Okay.
We're doing a deep dive into regenerative braking. It's this tech that really, well, supercharges EV efficiency.
It really does.
And our sources today, they really unpack how engineers are actually designing and optimizing these systems. Not with, physical parts at first,
Yeah.
but using this powerful tool called MATLAB Simulink.
Yeah, and what's really fascinating, I think, is that regenerative braking, it isn't just some buzzword you hear, right?
Right.
It's a genuinely clever system. It fundamentally changes how a car brakes.
I'll go.
Well, instead of just wasting all that forward motion, that kinetic energy, as heat through friction breaks the way cars always used to.
The old way, yeah?
Exactly. It actually recovers a chunk of that energy. The electric motor sort of runs in reverse, acting like a generator.
Sure.
And it converts that kinetic energy back into electrical energy. And here's the key part. It uses it to recharge the battery.
So braking actually puts juice back in.
Precisely. It's not a minor thing either. This significantly boosts an EV's overall efficiency and, crucially, its driving range. Every time you slow down or stop, it's a chance to get some energy back.
So what does this really mean for, for you listening, whether you drive an EV now or maybe you're thinking about one?
Well, it means understanding a bit of the sophisticated, almost invisible engineering that's happening.
Right, under the hood, so to speak.
Exactly. It makes these cars greener, more efficient, ultimately just more practical. And here's the kicker, like you said.
Yeah.
This whole complex design process, it happens before a single physical car part is even made.
That's wild. So it's all virtual first?
All virtual. Our sources really hammer this home. MATLAB Simulink provides this powerful and, importantly, risk-free environment to do all the vital modeling, the simulation, the analysis.
Risk-free because it's digital.
Exactly. Imagine finding a major design flaw virtually, something that might cost millions, maybe take years to find on a real prototype.
Oof, yeah.
And you fix it in maybe weeks on the computer. That's the kind of impact we're talking about. It's huge.
That really puts it into perspective.
And if you connect that to the bigger picture, using Simulink means engineers can visually design these really complex EV systems. They don't need to do tons of heavy line-by-line coding.
More visual, like building blocks.
Very much like that. And they can pull in real-world driving data, so the predictions they made are incredibly accurate.
Yeah.
And then they can test almost any scenario you can think of. Stop-and-go city traffic, steady highway cruising, even, climbing steep hills or going down them.
So you can really put the virtual car through its paces.
Absolutely. And it's crucial for figuring out how efficient that regenerative braking is in all those different conditions.
Mm-hmm.
And for tweaking the control strategies, how the car decides to brake to get the best balance between performance, efficiency, and, of course, safety and driver comfort.
That focus on real-world data and testing all those scenarios, that really shows the power here. But to actually build these virtual cars, these test beds, engineers need the basic parts, right? Mm-hmm. Digitally, I mean.
That's right.
So what are those key components they're modeling inside Simulink to make the simulation work?
Yeah, good question. To really simulate an EV powertrain accurately, especially with regenerative braking, you need several core components modeled in Simulink.
Okay, like what?
First up, you absolutely need a battery model. This simulates how a real battery behaves, typically lithium-ion these days.
Right.
So you're looking at its state of charge, basically, how full it is, like a fuel gauge, plus its voltage, the current flowing in and out, and even its thermal behavior, how it heats up and cools down, which is critical for battery life and safety.
Makes sense. What's next?
Then you need the electric motor and its controller. You model the specific type of motor, maybe a permanent magnet synchronous motor, a PMSM, which are very common and efficient, or maybe an induction motor. And you have to include its performance characteristics, things like its torque speed curve, which is like the motor's fingerprint, showing how much power it makes at different speeds, and its efficiency map.
Got it. Battery, motor.
Mm-hmm.
What else?
Then vehicle dynamics. This is huge. It accounts for all the real-world physics acting on the car, like rolling resistance from the tires on the road, aerodynamic drag, the wind pushing against the car, and even the road gradient, whether you're going uphill or downhill.
So how the car actually moves and what slows it down.
Precisely. And then, critically, the regenerative braking system itself needs its own model. This simulates how much braking force or torque it can generate, how much power it actually recovers, and the rate it feeds that power back into the battery.
Okay, that's the core system we're talking about.
Yes. And finally, you need drive cycle integration. This is where you use standardized driving patterns.
Patterns. Like test tracks.
Sort of, but they're data profiles representing typical driving. Things like the UDDS, that's the urban dynamometer driving schedule, think city driving, lots of stops and starts.
Right.
Or the WLTP, Worldwide Harmonized Light Vehicles Test Procedure, which is newer and tries to give a more realistic mix of city, suburban, highway driving.
So you test the virtual car on these virtual roads.
Exactly. It lets you simulate how the whole system performs under realistic operating conditions, not just, ideal lab conditions.
Okay, wow. So you've got all these detailed digital pieces, the battery, motor, physics, the regen system, these drive cycles. How do engineers actually, put it all together in Simulink? What's the workflow look like?
It's actually a pretty logical workflow, kind of like building with digital Legos, as you said earlier.
Okay.
Step one is to build the powertrain model. Basically, you create a block diagram in Simulink. You visually connect all those subsystems we just talked about: battery, motor, controller, maybe a transmission if it has one, vehicle dynamics.
Snap them together.
Exactly. You're building the car's core virtually. Step two, you incorporate the regenerative braking control logic. This is really where the smarts are.
The rules for braking.
Precisely. Using Simulink's control blocks, you define the key parameters. Like, at what point does regenerative braking kick in? How much braking should come from the motor versus the regular mechanical brakes? You need that blend to feel smooth.
The torque split.
Yeah.
That's the one.
And you also build in safety limits, situations where maybe regen shouldn't happen or needs to be limited.
Makes sense. Safety first.
Always. So once your virtual car is built and has its control logic, step three is run drive cycle simulations. You feed that standardized driving data, the UDDS or WLTP or others, into the model. You basically make the virtual car drive that course.
Okay, the virtual test drive.
Yep. And after the drive, step four is analyze the results. This is where you dig into the data.
What are you looking for?
Key metrics. How much energy did we actually recover, usually measured in kilowatt hours? What was the regenerative braking efficiency as a percentage? Some sources say well-tuned systems can hit maybe 70% recovery in city driving.
Wow, 70%. That's huge.
It can be in the right conditions. You also look at how much the battery's state of charge increased, and of course the bottom line. How much extra driving range did you get because of that recovered energy?
A late payoff.
Exactly. And then the final step, step five, is optimize parameters. It's iterative. You look in the results, you go back, you tweak the control algorithms, adjust the thresholds, the torque split, and you run the simulation again.
Fine tuning.
Constant fine-tuning. Trying to squeeze out maximum energy recovery, but always without messing up safety or making the braking feel weird or uncomfortable for the driver. It's always a balancing act.
That really sounds like an incredibly thorough and, powerful process. So taking a step back, what does all this simulation capability actually enable? What are the big practical applications for engineers working in the EV world? How does this virtual work translate into the actual cars we see?
Well, the applications are really significant, huge benefits. For starters, it's absolutely vital for EV design optimization.
How so?
It helps engineers figure out the best combination of components, what size motor works best with what size battery for a particular vehicle type. It lets them find the most efficient configuration right from the start.
Building the ideal powertrain on paper or screen first.
Precisely. It's also critical for control strategy development. Because it's so fast to simulate, they can test loads of different ideas for how the regenerative braking should work, making it more effective, smoother, more seamless to the driver, while grabbing as much energy as possible.
Better braking feel, more energy back.
You got it. Then there's range estimation. This is a big one for consumers.
Definitely. Range anxiety is real.
It is. So these simulations allow engineers to predict very accurately how far a vehicle will go on a charge, both with and without the benefit of regenerative braking factored in. That's crucial info.
Yeah, absolutely.
And finally, it supports comparative studies. They can easily compare, say, how much energy is saved in city driving versus highway driving, or compare different motor types or different control strategies head to head.
So data-driven decisions.
Completely. And the sources we looked at really emphasize this point. This whole simulation-first approach is low cost, it's risk-free compared to physical testing, and it's incredibly fast. It lets companies innovate much more quickly in EV tech, which is just invaluable in a field moving as fast as this one.
Yeah, it really feels like what we've seen today is how powerful this virtual modeling approach is, especially with tools like MATLAB Simulink. It's pushing the boundaries for EVs, making them more efficient, cheaper to develop, better for the environment.
Yeah.
And it all happens long before anyone picks up a wrench.
It's kind of a silent revolution happening on computers.
It really is.
And, This brings up, I think, an important closing thought.
Oh, yeah.
As the whole EV industry just keeps accelerating, getting really good at these kinds of Simulink-based simulations, it's not just another engineering skill anymore.
What is it then?
It's actually becoming a key differentiator for the engineers, for the researchers, for the companies. Mastering this virtual design and testing is fundamentally shaping the kinds of electric cars we're all going to be relying on in the very near future. It's becoming central to automotive innovation.